Okay, question 11. This one's about midway through a paper, so medium difficulty, but it does combine the data topic, so it's slightly more tricky. Data is not always everyone's favorite, and understandably so. Let's get right into it. A male runner is chosen at random. Okay, let's actually read the question. The cumulative frequency graph shows information about the times taken by 100 male runners and 100 female runners to finish the London Marathon. Okay, 100, okay. A male runner is chosen at random. So we're looking at this male graph. We have the graph. Find an estimate for the probability that this runner took less than 4 hours to finish the marathon. So less than 4 hours. We want to look at an hour 60 minutes. We're given the time in minutes. So 60 times 4 is 240. So we go up, find this little point here, and this little inaccuracy is why it's an estimate that looks to be 43. These are increments of 2, this being 50. It looks to be 43 out of the 100, finishing in 240 minutes. But obviously also we don't know how many finished on 240. So, but we aren't given that distinction here. So we have to assume it's 43 out of 100. And in this case, use a ruler with a sharp pencil to come across and see exactly, and always pay attention to increments. They don't like, they haven't marked the tens here, so like 19. So always be careful about that. Okay, 14, so a little sooner on in an exam. Maybe it might be slightly trickier. Let's have a look. This is another Venn diagram question. Perfect. An activity camp has climbing and sailing classes. 50 children attend the activity camp. 35 children do climbing. 10 do both. And 2 do neither. So, first thing we're going to do, ordering is going to be from here. We've drawn our two little circles. There are two things, climbing and sailing. I'm going to label them. Always label, because if you get them mixed around, that's 0 marks. Your examiner might be generous, might give you some for working, but good to be on the safe side. So I think the first thing after reading through the information is to identify that 2 do neither. So we'll leave these 2 out. Then we'll go back up and see that the information that talks about the intersecting bit, as I said, is the one that we should start with. So if you had started with this one, I mean, you would have gone nowhere. You don't know how these 50 are distributed, apart from that 2 are out here. The 35 in climbing, you don't know how they're distributed between climbing and sailing and just climbing. But the 10 you do know. That's the only one you know for certain. 10 doing, let's make that clear, it's a 10. 10 doing both climbing and sailing. 10. Now you can work backwards and see that this has to be 25. 25 plus 10 equals 35 to make a total of 35 doing climbing. And if you have a total of 50 in the climbing camp, you do 50 minus 25 plus 10 plus 2, leaving you with 13. And you can check this by doing 25 plus 10 plus 13 plus 2, which gives you 50. Now, a child attending the activity camp is selected at random. Find the probability that this child did exactly one class. So what are you going to do? Are you going to take 25, 13, and 10? Or take 25 and 13 out of 50 attending the activity camp? Always remember what your probability is out of. You're told up here, big arrow, 50 attend the activity camp. So it's 25 plus 13, 25 doing only climbing, 13 doing only sailing, out of 50. Oops. And this is 0.76. Or you can write it as a fraction. They both mean the same thing. Okay, last probability question that I'll be going through. This one is a bit more of a discussion question, which is why it's really important to understand the basics of probability. So Abby, Ben, and Carl Each drop a number of identical drawing pins and count how many land with the pin upwards. The table shows some of their results. Abby says, as a drawing pin can only land with its pin up or its pin down, the probability of a drawing pin landing pin up is a half. And you're probably saying, well, that doesn't really make sense. But if you think about it, it kind of could, but it doesn't. And there's a reason why. It's like saying you either win the lottery or you don't. Therefore, if you play the lottery, you have a 50-50 chance of winning. But what this does, this mistake, is that it says that with two events, you can have one or the other. Therefore, they're 50-50, forgetting that each event holds its own probability. In this case, if you look ahead, it looks like it's about 1/3 pin up and 2/3 pin down. But what Abby said, she's disregarded the individual probabilities that come with the event and just reduced it to two events on their own, forgetting everything that's enclosed within that event. So if you look at the mark scheme, what it says is outcomes not equally likely, which is basically what I've said. Next up, Carl's results give the best estimate of the probability of a drawing pin landing pin up. Explain why. And even if you can't really figure this out, what's different about Carl to the rest of his colleagues, we'll say. And the thing that's different is he's done way more trials. And even if you didn't figure that out, you can still sort of see he's done way more trials. That's the only thing that's different, and you can just put that down. But the reason that's correct is if you do more trials of an experiment, you're more likely to get accurate results, and outliers can be sort of blended in with the rest. Lastly, two pins are dropped. Estimate the probability that both pins land pin up. So here, if we use let's use Carl's results, that's about 35 over 100 of a landing pin up. So you have 35 over 100 for one, and then another 35 over 100. And this is going to come out to approximately, if you multiply that, 49 over 400. And that's your probability using Carl's results, which we have determined to be the most accurate.